Hello and thank you for being here. In this lecture, I'm gonna present an overview of relational database design that is a critical topic in database management systems. This presentation will guide you through the foundational concept and advanced technique for designing robust relational databases. We will study different forms of normalization for relational databases, like first normal form, then second, third, BCNF, fourth form, 5, and 6 that is not standardized yet. So let's dive in. Here we have a reference to a schema diagram for a university database. This schema will serve as a practical example throughout our discussion, and it will help us to apply theoretical concept to real-world context like universities database management. For example, we have tables like student, advisor, department, instructor, course, prerequisite, text, time slot, and each table has some attributes here, and this underscore, it means primary key. So now let's talk about database normalization. Database normalization is considered as a cornerstone of relational database design. This normalization can be defined as the process of structuring a relational database in accordance with a series of so-called normalized forms, and the objective is to reduce data redundancy and also to improve data integrity. The concept was pioneered by Edgar Frank Codd, who lived from 1923 to 2003. This normalization can involve synthesis, it means creating a new database design, or it can be decomposition, it means refining an existing one. Think of it as organizing your database to avoid duplication and ensure consistency. Let's look at an example of combined schema called ins department table, that is merging of instructor and department data. So this table, you can see we have attributes like ID, name, salary, department name, building, and budget. We have to repeat the department information like building and budget for each professor here that we have, right? So for example, Watson is repeated, this one here, right? Many times repeated. Or painter, right? So this is not optimal, we are repeating. And this repetition, it means the department details like building and budget appear multiple times for the same department. This kind of redundancy can lead to inefficiencies and inconsistencies, highlighting why we need careful design in order to avoid such kind of issues. So we are going to solve this issue using normalization in this presentation. Contrast that with a better approach. Consider combining two relations like section and classes, and in here we have like section ID, building, room number, and section we have course ID, section ID, semester, and year. So we bring these two in here, section as course ID, section ID, semester, year, building, and room number. This eliminates repetition, so each piece of information appears exactly once, making the schema cleaner and more efficient. This shows how thoughtful schema design can prevent redundancy right from the start. Next, we introduce functional dependency. This is a kind of constraint that defines how one attribute determines another one. We denote this one by arrow, like for example, we say ID, name, street, city, and salary. This means these data are dependent on this ID. Dependency, it means inclusively representation. So for example, we may have many Kim, but when we have this ID inclusive is designated for this one, right? So we say these information are dependent on this one. The functional dependency ensures that each ID maps exactly to one set of values, and in this way it can maintain data quality. Violating this, like having the same ID with different names, would confuse the database. So functional dependencies are critical for integrity. The composition may result into loss of information. Here is an example of lossy decomposition. It means we have splitting a table that causes problems. So this is our table and we have split it in two tables. So as we can see here, the two original tuples appears in this one and this one in the result along with two new tuples that incorrectly mix data values pertaining to the two employees named Kim. Although we have more tuples, we actually have less information. So we can indicate that a certain street like city, street, city, and celery pertain to someone called as Kim, but we are unable to distinguish which Kim exactly we are talking about. Thus, our composition is enabled to repeat certain important facts about the university employees. That's why we call it as lossy decomposition. Lossy decomposition introduces ambiguity, like not knowing which street goes to which ID. This underscores the importance of preserving information during decomposition. To avoid that, we use lossless-join decomposition. Consider a relation R with attributes of like A, B, and C that is decomposed to R1 and R2 like A, B, and B, C. So R1 has A and B and R2 has B and C attributes. The table shows values like alpha 1A and beta 2B. When we project onto A and B and C, then we join them back, we recover the original data table here, like exactly alpha A 1A and beta 2B. Here is the case of lossless join decomposition. We have the composed table R into two tables, and clearly we can see that we did not lose any information. This ensures no information is lost, maintaining the integrity of the data. So this lossless join is a key principle for safe decomposition in database design. Now let's overview the normal forms that we are going to cover in this presentation. Database normalization can be defined as the process of structuring the database in accordance with a series of normal forms. What is the goal? To reduce data redundancy and improve data integrity. These forms include first normal form, second normal form, third normal form. This is also called as 3.5 normal form, and it's called as Boyce-Codd normal form. Then we have fourth normal form, fifth normal form, and sixth normal form that is under consideration now. Each form builds on the previous one, addressing a specific type of anomalies and dependencies to ensure a robust database structure. We are going to explore each of these normalization forms in detail in order to understand their role in eliminating redundancy and also ensuring consistency. Now, let's start with the first normal form, or we call it as 1NF. So there are some rules here. Rule number one is atomic values. Rule number two is domains should be in the same type. Rule number three says unique name for each attribute and order. So we can say a table is in 1NF if it meets all these four rules, right? Atomic values meaning indivisible. Then all attributes in a column are in the same type. Each column has a unique name and order of data doesn't matter. What is the advantage here? Storage efficiency and no redundancy. Continuing with 1NF, the way domain elements are used matters. Atomicity is important here. It means how the elements of domain are used. So for example, this should be atomicity. It means we cannot divide it anymore, or this one we cannot divide it anymore, right? So if we try to split them into parts like CS and 0012 within the same attribute, we would violate atomicity. And also the same thing for here, right? Counterexample here is full name, right? Full name can be divided in first name and last name. Keeping values whole ensures clarity and prevents confusion during queries, reinforcing why atomicity is a core rule in 1NF. So here we can see that this data, we can have two data here, right? So this is violating, but here we have one. So this cannot be divided anymore, but this is not okay. So this column is not in 1NF because it is violating the atomicity. The second rule of 1NF requires that the column contains value of the same type, right? So here you can see all are in the same type, but this one is string. These are all string, but this one is integer, right? So this is not in the first NF. All values in the name column should be string representing names, and in ID they must be integer. Consistent types ensures predictable behavior when querying or updating the database. Rule number 3 says there must be unique name for each attribute. Like for example, here we have two attributes with the same name. They must have unique name. These clarify meaning and prevent errors during data retrieval, making the database more user-friendly. And in the last one, we say order doesn't matter here. So whether this park is here or here, it doesn't matter. This kind of flexibility simplifies database operations and ensure consistency regardless of how data is stored or displayed. Later, we can use a SQL query. We can easily fetch data in any order from a table. So in here, we want to normalize this table, right? So you can see here, one problem is here. We should split this record in two records. You can see here. So you can see OS is here, CN is here. But this one is okay. This one should be splitted in two records, C and C++. Moving to the second normal form, or you can say 2NF. A table is in 2NF if it is already in 1NF and it has no partial dependency. What is partial dependency? A partial dependency occurs when an attribute depends on only part of composite primary key. So in this table here, ID determines name, department name, and total credit. If department name depends on a subset of the key, that would be a partial dependency, which 2NF eliminates to reduce redundancy. It means every other column must be depends on ID. Let's formalize functional dependency. For a relation schema like R, if alpha is subset of R and beta is also subset of R, it means that if two tuples agree on alpha, they must agree on beta as well. For example, in a student table with ID, name, and total credits, ID and name, we like dependency like this. It means each ID uniquely identifies a name. This ensures that attributes depend on key, supporting 2NF's goal for eliminating partial dependency. Building on that, a superkey is a set of attributes that uniquely identifies all attributes in a relation. So then we have a candidate key. A candidate key is a minimal superkey. No subset of it is a superkey. In the ins department table with ID, name, salary, department name, building, and budget, So this department name and building is okay, ID and building is okay, but department name and salary is not okay. So salary has nothing with the department, right? So this suggests a dependency that might cause issue as department name is not a candidate. Here is an example of partial dependency. Suppose a table has a composite primary key of ID and course ID. Both of them are primary key. But the instructor attributes depends on only course ID, not ID here. This partial dependency violates 2NF because instructor does not rely on entire key. To fix this, we would separate instructor into a table tied to course ID, ensuring all non-key attributes depend on full primary key. So let's see how to resolve that. We move the instructor to a course table. You can see here, we call it as course table, and instructor like course ID into here, right? This eliminates the partial dependency, making both tables 2 and F compliant with no attributes depending on just part of the key. Next, we go for third normal form or 3NF in short. A table is in 3NF if it's already in 2NF, and if it is in 2NF, it means it's already in 1NF, and also it has no transitive dependency. Transitive dependency is a non-key attribute depends on another non-key attributes. In table that we have ID, name, department name, university ID, and university city, this university city depends on university ID, right? And this is not a primary key. This is called as transitive dependency and it violates 3NF. So we would like to fix it by moving university ID and university city to a separate table. So here, consider text table with ID, course ID, section, semester, year, exam grade, and total credits. The primary key is ID and course ID. Exam depends on course ID. And for example, Java has a practical exam, but math does not have a practical exam. So grade depends on exam here, not directly on the key, creating a transitive dependency. So in order to reach the 3NF, we would like to separate exam and grade into a table linked by course ID, and in this way we can remove the transitive link. So here is how we have splitted our table. This was the table. We have split it into ID, name, department name, and total credit for a student, course ID, title, and instructor for course and instructor, ID, course ID, grade, and exam for a student course, and exam score for the exam. Next, moving to Boyce-Codd normal form or BCNF, or I can say 3.NF. A table is in BCNF if for every functional dependency like alpha to beta, either beta is a subset of alpha, it means trivial, or alpha is a superkey. So in the case of inst department table, department name and building are related to each other. So we can say department name holds for building. Budget holds, but department name is not a super key here and it is violating BCNF. This can cause anomalies like updating a building for one department record but missing the others. This one here we are working with super keys. So super key is a kind of combination of attribute that uniquely identify any row within a table. We say that a table is in BCNF if it's already in 3NF, and for any dependency like A if B, A should be a super key. If in a table with a non-prime attribute like A and A determine a prime attribute B, it means it is violating BCNF. In the case of, for example, ins department, department name is a non-prime and department name determines building which is non-prime. So this is failing for BCNF. You can compare it with 3NF which allows non-prime to non-prime dependency. It was okay. But BCNF is stricter, ensuring no anomalies from functional dependency. In BCNF, a prime attribute should not be dependent on a non-prime attribute. Here is a table with ID, course ID, and instructor. The primary key here is ID and course ID. One student like 210101 is enrolled in two courses, 001, 002 by Park and Lee. The functional dependency of ID, like course ID to instructor here, is fine, but we will check if instructor course ID holds, which could violate BCNF as instructor is not a super key here. Once again, a student can enroll for multiple courses, right? We can go for example, this course is Java and this course is Python with two professors, right? For each course, an instructor is assigned to a student, like Professor Park for Java, Professor Lee for Python. There can be multiple instructors teaching one course like 01. And here is the problem, that instructor course ID not hold. Instructor depends on course ID. So this course ID depends on instructor, and instructor is not a super key. That's why this is the problem for BCNF. Continuing with the table, the primary key is ID and course ID. So it satisfies already 1NF because all values are atomic, attributes are unique, and domains are consistent. It is also in 2NF with no partial dependency, and also it is in 3NF with no transitive dependency. But we need to check whether it is in BCNF or not, particularly regarding the instructor and course ID. The primary key here is ID and course ID. One instructor teaches only one course, but one course may have two different instructors, as you can see here. So here there is a dependency between course and instructor, where course depends on the instructor name, and this is not a key. The dependency instructor course ID holds, meaning each instructor teaches one course, but instructor is a non-prime attribute and course ID is a prime attribute and it violates BCNF. This could cause anomalies like if we update the course for one instructor in one row but not for the others. So BCNF requires that only super key determine other attributes. So here is the solution. In order to solve this problem, we decompose into two tables, this table into two tables. So in here we have ID and instructor ID, student ID, instructor ID, and in here we have instructor ID, instructor name, and course ID. This eliminates the problematic dependency. It means as instructor no longer determines course ID in the same table. Both tables now are in BCNF, ensuring no anomalies from functional dependency. Now we move to fourth NF or fourth normal form. A table is in 4NF if it's already in BCNF and it has no multi-value dependency. What is multi-value dependency? Multi-value dependency occurs when for a single value like A, there are multiple values of B independent of C. So in a table like R, A, B, C, if A multi-determines B, B and C must be independent. So 4NF requires at least 3 attributes to apply. So here is an example issue. A table with course ID and hobby attributes where hobbies repeat for each student. So you can see for each student we are repeating the hobbies. There is no relationship between course ID and hobby here. Hobbies are tied with student only, not the course. This multi-value dependency violates 4NF as course ID multi-determines hobby, creating redundancy and potential inconsistency. So, repeating hobbies is the problem here and leads to unnecessary repetition of data and other anomalies as well. So we will decompose these two tables in one ID and course ID and also ID and hobby, right? Then we can connect these two tables and make some queries. This separates the independent multi-value dependencies, ensuring the database is in 4NF with no unnecessary repetition. Let's apply this concept to a real-world example, like a video library database. Assume a video library maintains database of movies rented out. Without any normalization, all information are stored in one table as we can see here, like for example, full name, physical address, movie rented, salutation, and category. So for example, this Janet Jones rented Pirates of the Caribbean and Clash of the Titans movies, both action movies. So we have repeated action movie here. This is a kind of redundancy. And also, multiple movies and categories are listed in a single cell. You can see here, this is violating first NF atomicity rule. So to reach 1NF, we have to ensure atomicity. So you can see here, each movie is in a separate row and each cell contains a single value like action and romance and these things, right? We notice an issue here. Robert Field, you can see here, Robert Field appears twice with different addresses here, indicating two distinct people. We use a composite key like a full name and physical address to uniquely identify records. So for the 2NF, we need a single column primary key and no partial dependencies. We created a member table and also movie tables here. The member table is with membership ID as the primary key, and we have full name, physical address, and salutation, and we store them once. Then we have a movie table here. These links with membership ID, these two tables are connected with each other. For example, membership 1, he has movies rented here and the information are here. This eliminates partial dependency as all attributes depend on full key. Here, membership ID acts as a foreign key in the movie tables and it links back to the members table. For instance, membership with ID 1 corresponds to Janet Jones, who rented these movies, two movies. And foreign key maintains relation between tables, and also this foreign key ensures referential integrity as we normalize further. So in here we have membership ID as a foreign key and membership ID is here as the primary key. So here we have a problem with repetition here as we are repeating the salutation. Now we spot a transitive dependency in member table. Changing full name here might affect the salutation. So for example, updating a name could require updating Mr. or Mrs. as well. This violates 3NF as salutation depends on full name, not directly on membership ID here. This is a kind of transitive dependency. Transitive dependencies like this can cause update anomalies. It means changing a non-key column might cause any of other non-key columns to change. So to reach 3NF in this table, we have to eliminate transitive dependencies. The members table now has membership ID, full name, physical address, and salutation ID linking to a salutation table that we make it here with like Mr., Miss, Mrs., and Doctor. And also we have the movies tables remain unchanged, membership ID and movie rented. This ensures no non-key attribute depends on another, and in here we can achieve 3 normalization 4. Beyond 3 normalization 4, we have BCNF, which address anomalies from multiple candidate keys. Sometimes we call it as 3.5 normalization 4. Then we have 4NF that eliminates multi-value dependencies, and this ensure no independent multi-value data. Then we have 5NF, this prevents lossy decomposition, and 6NF, though not standardized yet, it's discussed for future use. Each form tackles specific issues to make the database as robust as possible. So in summary, the first NF ensures atomicity, unique names, and same domains, and order also not important. Then second NF removes partial dependency. 3NF eliminates transitive dependency. BCNF or 3.5NF address non-prime dependency. 4NF tackles multi-value dependency. 5NF ensures no lossy decomposition. We have to be in somewhere that we cannot split our tables anymore. And 6NF is still under discussion. Each form builds on the previous one and they refine the database structure. Okay, thank you very much for your attention. Please practice and feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.